Imagine flipping the switch on a brand new multi-million-dollar rock crushing plant on day one, only to realize your machinery is just drastically underpowered, and your silos hold like 40% less material than you planned.
Yeah, it sounds like a complete nightmare, but I mean, it happens in the field all the time.
Right. Today we are doing a deep dive into the Rock Mechanics Blueprint PDF. We're going to walk you through this exactly as if we were presenting a highly technical professional slide deck to you. So, okay, let's unpack this.
Well, to set the stage here, every plant decision is written in the rock. You just can't cheat the geology. Guessing rather than testing these 8 physical properties, it routinely leads to those underpowered crushers and premature failures you just mentioned.
Yeah, totally. So on this slide, we see the engineer's diagnostic toolkit. It introduces these 3 critical buckets, which are sizing and energy, wear and maintenance, and product qualification.
Exactly. You have to nail all 3 of those buckets to succeed.
Right. So moving to the next slide, let's look at sizing and density. I was honestly blown away by this 40% margin of error thing.
Oh, it is a massive pitfall. See, when calculating silent capacity, engineers sometimes base it on solid density.
Which is like the theoretical volume of a solid, unbroken block of rock.
Right, exactly. But they really should be using bulk density, because that accounts for the literal air gaps between the broken pieces of rock. If you ignore those air gaps, you can overstate your capacity by up to 40%.
Wow. So solid density is like measuring the exact volume of your clothes, but bulk density is the actual larger space they take up when thrown haphazardly into a suitcase.
Yeah, that is a perfect analogy. You have to account for the awkward gaps. And that same precision, it applies to power sizing too, using the bond work index.
Oh, the WI metric.
Yes. So a plant processing rock that takes, say, 7 kilowatt hours per ton requires 75% more electrical power than one processing 4 kilowatt hour per ton rock.
Wait, 75% more?
Yes, just to get the exact same throughput.
Just for the exact same amount of rock. That is wild. Okay, so moving to the next slide, we tackle wear and maintenance. There's a staggering stat here. A manganese jaw plate crushing limestone survives 15 times longer than one crushing granite.
Yeah, the wear difference is just extreme.
But wait, isn't harder rock always more abrasive? How does that work?
Well, what's fascinating here is a phenomenon we see on the field diagnostics slide called the Basalt Paradox.
Basalt Paradox. Okay, I'm listening.
Right. So basalt has massive uniaxial compressive strength. We're talking like 300 to 400 megapascals due to these tightly interlocked crystals. It is incredibly hard to break, but its abrasiveness is surprisingly low because it lacks free quartz.
Oh, I see. So Mohs hardness and crushing energy are complementary metrics, not substitutes.
Precisely. It takes huge energy to crush basalt, but without those sharp, glassy quartz particles, it won't necessarily just chew right through your steel liners.
That makes so much sense. Okay, moving to the next slide. Let's examine qualifying the aggregate. So we've managed to break the rock without destroying the machines, but it has to meet tight construction specs, right?
Exactly. And for that, we rely on the Los Angeles Abrasion Test. You put your finished aggregate into a rotating drum with steel balls for 500 rotations.
And then you just measure how much mass gets pulverized.
Right. And if you are supplying aggregate for high-traffic asphalt, that loss must be 25% or less. But durability is really only half the battle. We also have to measure cubicity.
Right, the shape of the rock. Because the document points out that if your aggregate has over 15% flat or elongated pieces, that's really bad news.
It is, because those flat pieces act like weak shear planes. Imagine heavy wheel loads driving over asphalt made with flat rocks. They just snap under the pressure.
Oh, wow, creating noticeable air voids under the surface.
Yep, and the pavement will literally shed and degrade over time. You often have to physically tune the plant, like choke feeding the crushers, to force the rock into blockier shapes.
Man, so what does this all mean? Basically, a crushing plant's success relies strictly on respecting these technical rock parameters, from the energy it takes to break it to the exact geometry it forms when it shatters.
It really does, and I'd leave you with this final thought to kind of build on that. If these physical rock properties dictate everything from motor sizing to maintenance schedules, how long until we see real-time AI sensors mounted directly on crushers?
Oh, like dynamically adjusting the plant's close-side settings on the fly as the rock changes.
Exactly. Rather than waiting days for lab results, the machine just adapts automatically. It's the logical next step for the industry.